How did Dutch engineers build a giant arch full of apartments on top of a swamp?
This one had 3 stories worth of mud, to the point where the workers actually had to wear wetsuits.
What happened when a rock-shaped opera house was built using the most modern and ancient techniques?
Anyone can build a symmetrical auditorium, but here they went weird and wobbly to build something exceptional.
And how was a piece of British history re-engineered for the 21st century?
That is 315 tons of glass and 478 tons of steel.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Rotterdam in the Netherlands is one of the biggest ports in the world. Crisscrossed with canals, rivers and docks, water is the lifeblood of this city. However, if you're a builder, this water is much less welcome and something you'd better have a plan for. So when the city wanted to build a massive new horseshoe-shaped structure with 4 floors of underground parking right by the docks, Dutch engineers had to use all the tricks in the book to make it possible.
This building not only has the visible engineering marvel of a huge unsupported arch, but equally impressive is that they built this into a swamp.
Specialist builders had to dive deep down in a muddy lake to build foundations. Clever concreters created an incredible 12-story high arch, which engineers crowned with extraordinary apartments, apparently built on thin air. These penthouses covered dozens of buzzing market stalls, restaurants and shops. And at each end are the largest cable net windows in Europe. This is Rotterdam's Markthal, or Market Hall. So how did they build it? Following German bombing in World War II, Rotterdam's flattened city centre had been redeveloped, but somehow it had lost its soul.
Rotterdam was planned after the war in a very functional way where they separated living and working and shopping.
And business-like.
Exactly, so they realized, hey, maybe we should combine it because it's not that great to separate.
To liven things up, the city challenged architects to design a permanent covered market with hundreds of new homes either side of it.
So the program demands for 2 slabs of housing and somewhere in between a market hall. I said to them, yeah, but that's boring. So instead of having this with the 2 slabs and then a market hall in between, I said, well, why don't we turn it upside down so that you have slabs on either side and you have more penthouses here and you have a big hall, like a space where you can breathe and where you can monumentalize and good food.
The final approved design was an ingenious merging of housing and markets where not a square centimetre of space was wasted. It would all be built on massive 4-story deep foundations the size of 2 football pitches, dug out of waterlogged ground and waterproofed with concrete. On top, 228 apartments cast in concrete would be stacked like huge bricks, creating the arch walls with a final top floor of penthouses that lock it all together and create the roof. Cladding inside the huge 34-metre-high tunnel would create the largest work of art in the world. Finally, at each end, a grid of cables would support hundreds of panes of glass, protecting the market stalls and cafes inside from the weather.
They've made an entire building in this arched form,
and they've managed to dot apartments and rooms throughout it. It's a really interesting and quite fun piece of engineering.
Building the Markthal would require exceptional engineering skills right from the beginning. The ground is so waterlogged here, anything built below ground level acts like a boat on water.
The basement is actually like a bath at home, and you would take a bucket and try to push the empty bucket into the water. You have to apply a lot of force. And if you push it really down and you let it go, it will jump upwards. And the piles, they have to prevent the basement actually jumping upwards.
To counter this extraordinary upwards force, engineers had to rethink the role of the foundations. Rotterdam is completely waterlogged just 2 meters below the surface. A 4-story deep basement car park the size of 2 football pitches creates vast water pressure underneath it. So long concrete foundation piles would be built down to grip into the soil below, stopping the structure rising. But there's also pressure on the sides. To counter this, a huge concrete grid would be built to hold the walls back. This extreme water pressure and the sheer scale of the building's footprint meant these foundations would be some of the most complex ever built in the Netherlands. Work began in 2009 as the site was cleared and a retaining wall was created using a combination of interlocking steel sheets and tubes hammered in around the edge, making a strong, waterproof perimeter. Then, inside the perimeter, the main foundation piles were made by first driving huge pipes to a depth of 30 meters. An impact hammer slowly but noisily pushed each pile into the soft ground. With over 2,000 piles needed, it was a slow and disruptive process for the locals.
It contains about 2,500 concrete piles to build the foundation, and there was a lot of noise, you know. So they make a wall of, I think it was about 200 containers to reduce the noise. Cracks in the walls, surrounding buildings, so it had a lot of troubles before it got here.
With the pipes hammered the 30 meters down, concrete was poured in to give the building its strong, deep roots. Once set, the tips of these piles were revealed and a massive concrete grid built on top. This will perform a temporary engineering function by bracing the retaining walls against the huge pressure from outside as the engineers dig down a further 11 meters. And this is when building in the Netherlands gets really difficult.
As soon as you dig like 2 meters deep on this location, you will find water. The whole basement with 4 stories underneath the ground level is like building something underwater. It's a kind of underwater building.
As the winter of 2010 progressed, the site became flooded. But instead of being a disaster, it was all part of the plan. The huge grid now underwater was supporting the walls at the top. But as they dug down, the lower part of the walls, which aren't supported, could collapse. This is where the floodwater comes in.
The water inside the basement, it gives a kind of counter pressure. Actually, it gives exactly the same counter pressure as the pressure from the outside.
If the excavators dug down without water inside, pressure from outside would have pushed against the lower dam walls, and eventually the sides would have caved in. The water stopped that, but made for hard work. For months, excavator operators worked blind, only computer screens telling them where to dig. Eventually, all 160,000 cubic meters of material, the equivalent of 64 Olympic swimming pools, had been excavated. Now the engineers had to prepare the bottom of the foundation pit for waterproof concreting, with 15 meters of muddy water still in place. It was time for a very specialized team to get involved.
They continued building, but with builders in wetsuits. This is the most unusual but ingenious method for building foundations.
Highly skilled construction divers swam down to install steel at the bottom of the lake. The piles that formed the foundations needed reinforcing steel attached. This steel would knit together all the piles and the first layer of concrete. Once this was set, it would lock together with the grid above, creating a super strong waterproof box, rigid enough to resist the water pressure from the sides.
Construction workers were putting that reinforcement in place, making the connections between the underwater concrete and the piles, and doing all stuff like that. There were specialized divers which could stay down for a couple of hours and then had to come up again and be refreshed.
Like the excavators, the divers couldn't see what they were doing.
Construction sites are typically dangerous places as it is, let alone this one that had 3 stories worth of a mud pool.
We see very little under the water. A lot of our job is done by feel, so it's basically touch and movement, and generally we have to navigate by it's a mental map in our mind rather than using points of reference.
With the steel reinforcement in position, the next crucial step was to pour the waterproofing concrete so the site could be drained. Extraordinarily, this was achieved by pouring wet concrete into the water.
It might seem surprising, but properly mixed concrete can set just as quickly underwater as it can on land, as long as it's poured gently and it's not agitated during setting. And that's because it's nothing to do with drying. It's actually a chemical reaction that naturally expels water.
For 72 continuous hours, 1,500 loads of waterproof concrete were delivered, laying down a 1.5-meter thick layer to seal the floor of the foundation tank.
After the concrete is set, you can pump out the water. Then you have your empty building pit.
It took 2 weeks to pump out 14 million liters of water. Then the 4 layers of car park floors were poured, and the massively strong 3-dimensional foundation grid was complete. Now the 12-story Markthal could be built. Right at the start, the architects had the vision that a roof for the market would be provided by building a huge arch. An idea that won approval from the structural engineers.
Arches can take many times their own weight, and that's because they use their own weight and gravity as the source of their strength.
Arches are a very efficient structure. They span a gap and they convert whatever load is on that arch into pure compression within the arch and take it down to the ground.
The Romans were already using that. They made concrete and brick arches for bridges and domes. When it's there, it really works well. The trick is how to make it.
Building an arch means creating a curved shape, which is good for strength, but bad when 228 apartments have to fit neatly inside the arch itself. To start with, the engineers took a conventional approach.
In Holland, the construction technique used for apartment buildings is often something called a tunnel form construction technique. It's a set of walls and floors in which you can pour the concrete and thus realize the walls and floors in one go.
Tunnel shuttering uses these large boxes that act as molds, what we call formwork. And these molds, you pour the concrete around. And once the concrete is set, you can just slide these molds out and use them again in another room. So this means that we're saving time, we're saving money, not having to create new pieces of formwork every time.
To speed things up even more, the engineers used technology to keep tabs on exactly when they could move the build forward.
There is a system monitoring the setting of the concrete, And you can read out the results through Wi-Fi or mobile network. So the contractor could see the setting of the concrete from his office and know when he could take the next steps in the construction.
This technology and the repeated shapes of tunnel form construction allowed the floors to be built up super quickly. But how did the engineers make the arch walls curve out and then in as they went up?
We thought of using the apartments as kind of bricks in the arch. Putting the bricks, every step putting the bricks a bit closer, closes the gap already for a large part.
The structural effect of this stepped stacking of apartments is especially plain to see for residents who live higher up in the curve of the arch.
Yeah, you cannot hang stuff in particular maybe on these things. You always have to kind of find a way. So shelves are not really working that well, but pictures still do.
By mid-2013, with the sides of the arch complete, the last apartments to be built would be the exclusive penthouses, forming the flattest part of the arch and the roof of the covered market. Up until now, the build had relied on the apartment below supporting the one on top. But in order to create the arch, engineers had to figure out how to support these penthouses while they built them, 37 meters in the air and over the whole 120-meter length of the hall.
Filling this whole space with a temporary structure would be a project on its own. It would be very costly, it would take a lot of time. So that was the reason to try to eliminate it. So the whole temporary support structure was put on wheels on a crane.
This structure is essentially a reinforced tower set on some tracks. This means that as the roof sections are poured and allowed to set, we can move the structure along the building.
One at a time, floors were craned in and then concrete poured to build up the penthouse structures. When complete, they made up the most crucial engineering blocks in the entire building.
If you have an old-fashioned arch, you will have bricks coming up, and then in the end you have a kind of closing stone filling that gap. The penthouses are actually that kind of closing stone.
Today, the residents of these roof section penthouses enjoy peerless city views and can literally look down on their neighbors.
It's very special because you see all the shops downstairs and you can see the people around you, so yeah, it's nice. Hi there! You see, he likes it.
By early 2014, the project had reached its final stage. Cladding smoothed the outside walls, and the 4,000 aluminium panels inside were each printed with part of a giant mural. The Horn of Plenty was created by Dutch artist Arno Koernen, and at 11,000 square meters, lays claim to being the largest artwork in the world. All that was left to complete this cathedral to food was to weatherproof it with a wall of windows at each end. The designers were determined to retain the openness of an outdoor market and keep the incredible artwork on show from outside. The problem was, Rotterdam's windy weather meant traditional windows this big would need thick frames to remain rigid and prevent the glass from shattering. So the engineers found another, more flexible way.
So it has to be closed, and so no columns. How can I do that? I said, yeah, well, you can make cables.
An array of windows supported by a grid of cables is called a cable net facade. At 630 square meters each, the ones they built here are the biggest in Europe.
The principle of a cable net facade is very similar to a tennis racket, where you have steel cables that are like strings, and then you have glass mounted between them. And this gives the strength, but also the flexibility that's needed for covering an area of this size.
Like the strings on a tennis racket, the cables in the facade must be extremely tight to work. With the 48 cables in place, they were then stretched tight so they could withstand pressure from the wind. Each 3-centimetre thick cable was pre-tensioned by around 30 tons, causing it to lengthen by up to 15 centimetres. Then specialised joints were mounted onto the cable intersections. Here, the glass was clamped on at the corners. These joints, the cables, and the silicon between the glass panels allow for an extraordinary amount of flex in this giant window.
And I'm aware it was quite a work for the engineers to make the joint, because when there is a storm, say wind force 11 or something like that, then it goes in and out for more than a meter.
In December 2014, Markthal's doors were finally thrown open to the public. And they've kept on coming ever since, at a rate of around 20,000 every day.
It's now 5 years old, and the amount of visitors keeps more or less steady around at 8 million, which is actually more than the Eiffel Tower, I can tell you.
By making this multi-purpose market hall possible, its builders have helped start something big in Rotterdam.
It's a real piece of art that they put here together, and we really like it.
It's an amazing piece of construction work. It's also an amazing civic place because it's for everybody.
It may have taken 5 years to rise from the mud, but Markthal now stands as rock-solid evidence of how great engineering and design can be a powerful force for change. "120 kilometers northwest of Hong Kong, in southern China, the brand new megacity of Guangzhou wanted to get noticed. It decided the answer was an incredible new building that would draw the attention of the world. They turned to a legendary architect with a reputation for designing the impossible. Zaha Hadid didn't disappoint. Dreaming up one of the most advanced buildings in the world. Building a gigantic steel frame with techniques that are millennia old. Mimicking natural forms with mathematical wizardry. And redefining the traditional shape of a concert hall that has gone unchallenged for decades.
Anyone can build a symmetrical auditorium, but here they went weird and wobbly to build something exceptional.
This radical design is the Guangzhou Opera House. So how did they build it? The city of Guangzhou is a giant metropolitan center, home to 25 million people, over 3 times the population of New York. In 2002, the regional government commissioned a new centerpiece that would hold its own amongst the city's gleaming skyscrapers. A $200 million opera house. It was designed by the late Zaha Hadid, an architect whose visions pushed at the boundaries of engineering. She found her inspiration just a stone's throw away on the banks of the Pearl River. Simon Yu was the project architect overseeing its construction.
We had this concept of these 2 pebbles by the river, so it's like placed on the river banks, and with the sort of water that sort of washes over it, or these pebbles which are dragged along the sort of the river bank.
The inspiration may have been simple, but it meant creating one of the most advanced buildings in the world.
When you're emulating a natural shape, the first things that go out of the window are symmetry and repetition.
The complex would be made up of 2 auditoriums, a smaller 400-seater, and next door, the larger Opera House, able to seat 1,800 people in its acoustically perfect hall. Both buildings would be cloaked in a net of 12,000 tons of steel frame triangles, joined together by 59 huge, specially designed connectors, creating a strong enough frame for the building's exterior coat. Each is then covered in a jigsaw puzzle of over 75,000 unique hand-cut granite triangles to complete the stunning vision of two pebbles on a riverbank. The engineers started with the simple bit, making the two concrete structures that would house the concert halls. These went up quickly using tried and tested techniques. The first major obstacle came in the form of the giant steel enclosure that wraps the cement structures, a vital part in creating the building's shape.
The Guangzhou Opera House is very clever because it feels like something that's fluid and light, very free-flowing, much like its pebble inspiration. But underneath its curvy skin, it's packing some very, very sophisticated geometry and engineering.
The answer to building the extraordinary 43-meter-tall, 120-meter-wide pebble-shaped shell lay in the humble triangle.
Despite competition from circles, triangles are actually the strongest shape. They're able to distribute the load evenly throughout all three sides. And so because of this, here is really the best shape for evenly distributing the load, carrying it all the way down to the ground of the structure.
To create these triangles, the engineers needed to design and build 59 unique star-shaped joints called knuckles. The incredibly complex design relied on the power of the computer. But for manufacturing them, they turned to an ancient technique called sand casting.
The way they were made was actually quite an old-fashioned way. It was very, very simple in the sense that they actually would make a one-to-one version of these steel members in wood.
To create steel joints using sand casting, the engineers first made the exact shape out of wood. In a foundry, this wooden shape is sandwiched between two layers of sand. The wood is removed, leaving a perfect imprint, creating the mold. Then, molten metal is poured in. It hardens, and when the sand is removed, a steel version of the wooden shape is revealed.
These knuckles were actually all absolutely unique, and they have a very, very tough job of keeping and bracing all these, a lot of the steel together. You know, they all work together.
All the knuckles combine to form the super strong outer shell.
Sand casting, it sounds like really old-fashioned, right? But in this instance, it really is a case of if it ain't broke, don't fix it. The Shang dynasty were using this technique in 1300 BC, and it's still in use today to make one-off pieces.
With the frame in place, the next challenge was creating the pebble-like exterior. The solution lay in yet more triangles, each individually cut to cover the 12,000-ton steel frame. It would be an impressive effect, but an engineering nightmare. To mimic the natural shape of a river-washed pebble, every triangle had to be cut to exact specifications that changed constantly. To make things even harder, the clients loved the idea of the pebble so much, they wanted the building clad in super heavy, super hard granite.
The total granite facade cladding area is 24,700 meters squared, with 75,422 separate pieces. That is essentially the jigsaw puzzle from hell.
The engineers had all 75,000 pieces of stone cut to size off-site. Every tile had a tolerance of 5 millimeters, and lasers were used to make sure each was precisely placed. With the outer shell complete, the engineers turned their laser sights on the sky lobby, an area between the concert halls and the outer shell, where the designers wanted to create a futuristic space with floating walkways with no visible support. The solution hidden inside these impossible balconies are a secret collection of steel boxes, anchored to the building's sturdy concrete core, that support the structures, giving the illusion of weightlessness. They are covered with white organic cladding, created in huge computer-designed molds that were filled with white gypsum plaster and anchored to the steel and concrete frame, piece by piece.
These two separate structures, this self-supporting outer ring and the inner concrete structures, creates this space in the middle that appears to be completely unsupported. And this allowed the architects to play around with these floating staircases and these cantilevered levels that appear to completely defy gravity.
The real challenge, though, lay in creating the concert hall itself. Because to create perfect sound, concert halls are traditionally perfectly symmetrical. This is anything but. The key lay in controlling how the sound bounces around inside the hall.
The art of acoustics is getting the reverberation just right. If there's too little a gap, then everything sounds quite flat. But if there's too long a gap, then you get echoes, and it sounds quite muddy.
They turned to one of the world's leading acoustic engineers to pull it off.
Getting the reflection sequences right, that's the sound that hits the wall or hits the ceiling and ends up at the audience, is vitally important because it adds to the strength of the sound. It can add to the clarity of the sound.
The way you do that is by building what's called a shoebox shape. The sound bounces off the walls and back to the audience. The problem is that the bigger the auditorium, the further the audience is from the stage and the worse the view. But if you fan the audience out, the quality of sound deteriorates. With an 1,800 seat capacity, this space would be huge. So Peter and the team had to find a way to keep the audience close and the sound spot on.
One of the alternatives is asymmetry, where you can use the side walls of the asymmetrical hall to reflect the sound in a way that is similar to a shoebox, that you enforce the lateral reflections.
So the plan was to create curved walls and surfaces within the auditorium to bounce the sound to exactly where the engineers wanted it. But figuring out how to do this was so complicated, Peter and the team decided to build a model of the hall where they could test this out.
In the scale model, you can't test at every seat, but you use dummy heads and microphones to test at a sample, but also you test where you think you're potentially going to have a problem.
By analyzing the sound recorded on the tiny microphones in the different positions, the team were able to build up a picture of exactly how to shape the inside of the hall.
What we were looking for in the model was strong focused reflections from concave surfaces, but also the presence of multiple reflections which will give you the effect of an echo. And such a complex space that this was the only way we felt at that stage we could do it.
By bending and curving the walls, Peter and his team were able to create an amazing sound and not compromise the view. The result of all these complex solutions to engineering problems is a building inspired by nature that is truly out of this world.
This building for me is a perfect example of what happens when architects and engineers and all sorts of other experts work together to challenge the ordinary and the simple.
In the heart of London, engineers and architects faced a problem. How to make a 180-year-old building find its place in the modern world. The solution was a breathtaking revamp, which meant demolishing 2 acres of the old structure and using mathematical precision, replacing it with an 800-ton roof of steel and glass. This is the Great Court of the British Museum. So how did they build it? At the turn of the century, the British Museum was in dire need of modernization. The center of the museum was a cluster of small and confusing rooms, and with nearly 7 million visitors a year struggling to see its 50,000 items, the time had come for change. But transforming a building that's almost 200 years old is a very different proposition from building one from scratch.
Working with an old building can be a nightmare. You never know what you're gonna find or what problems you might run into.
The man tasked with the challenge was one of the world's leading architects responsible for the Millennium Bridge and the Millau Viaduct.
To get from one gallery to another, you'd have to plow through the gallery. So it was a constant traffic jam, and it wasn't very pleasant.
Lord Foster's solution to this maze was to knock it down and create an enormous open space between the exterior facades and circular library in the middle. Over that would go a show-stopping glass roof to create the largest covered square in Europe.
If you then imagine kind of surgically, you take all that stuff around the great circular library, and you've suddenly got breathing space. You've got a vast space. How do you put this glass umbrella so it will evaporate and it's like an artificial sky?
The plan? To demolish the massive rooms filling the area outside the central round library, then to reinforce its foundations, before building a protective shell around the reading room and shore up the exterior walls, ready to receive the 800-ton roof made up of almost 5,000 pieces of steel and over 3,000 panes of glass. No two would be the same. In 1998, with the exhibits moved into storage and the books from the reading room moved to the British Library, work began on demolition and shoring up the 180-year-old foundations.
At the time, the Great Court project was a complete rebuild inside of the courtyard.
Pulling this off, though, was full of risks. They had to strengthen the almost non-existent foundations by pumping concrete 2 stories under the reading room, creating a reinforced slab for it to sit on, and excavating a new basement underneath.
The reading room is a very early, delicate cast iron frame with a very beautiful and listed papier-mâché ceiling. And papier-mâché is dry and very, very delicate, very prone to cracking. So as we dug, you didn't want any movements, or you could easily have cracks appear.
The library sat on shallow foundations that would never take the weight of the roof. So stage 1 was to underpin it by pumping in thousands of tons of concrete. Even this was a delicate operation. Knowing the work could disturb the structure above, alarms were installed. And it turns out, for good reason.
I remember the message coming back, oops, the alarms have gone off. We seem to be lifting the reading room. We'd better stop. And the pumping had got a bit carried away and started moving the reading room upwards.
Can you imagine being the engineers at this point where you've got a precious piece of English history that's stood there for hundreds of years and now it's at risk of being quite seriously damaged?
The next major engineering challenge was that the very delicate central reading room was nowhere near strong enough to carry the weight of the new roof.
In order to keep the heavy weight off the central reading room, we didn't want to load the roof onto the central reading room. So we had put in a ring of columns. They had never got a proper skin on the reading room. It was very ordinary brick. It was never designed to be seen, so it needed a new skin. What Foster's cleverly did was leave a little gap between the new stone and the existing brick. And in that gap, we put 20 new columns and a whole load of cross-bracing to stabilize those 20 columns. And that gave us a beautiful place to take the weight of the roof. And by putting the cross-bracing in it, it also wasn't going to wobble sideways. So it was a really stable core, and nobody even knows it's there. It's all hidden behind the stone.
So, with the foundations in place, the engineers were able to build a hidden steel structure around the central library that would carry the weight of the roof. The library itself would sit safely inside, and then it would all be hidden in the new external finish to the library. Finally, the old building was ready to take the weight of the new glass roof. However, designing a curved glass roof that would join the square outer walls to the circular library was a serious mathematical headache.
I think you have to go and see the roof to kind of understand why it's complicated.
It looks floaty, light, effortless, but that is 315 tons of glass and 478 tons of steel.
The team needed help to realize the design. They turned to computer power.
At a time when we were only just getting used to our computers, really in terms of defining complicated geometries. Now, 20 years on, it's pretty easy, but it wasn't then.
The computer enables you to see the implication of one or several variables, making it possible to create something that is one and the same time extraordinarily complex, but to make it look incredibly simple and, in the end, poetic.
With the geometry of each piece of glass and steel calculated, the engineers got to work transferring it from the computer to the courtyard, starting with building the 2-acre mesh of steel.
So it's a new structure at the circular heart of this. And then all that very delicate tracery of steel members, 11 kilometers in total length, making over 3,300 triangles. And that whole thing can move. It can expand, it can contract, it can absorb snow loads, it can move, and it's only delivering vertical loads onto the historic fabric.
The team then installed the 3,312 panels of glass. With no two pieces the same, it was an enormous jigsaw puzzle to complete.
It's like an iceberg. You're seeing the tip. What you're not seeing is that extraordinary body of work by so many individuals, the people who made it.
Finally, on December the 6th, 2000, the Great Court opened to the public.
It's the largest covered public square in Europe. An incredible piece of engineering.
The new courtyard with its floating glass roof is the result of thousands of man-hours from Lord Foster's team of designers, builders, and engineers. The result is an extraordinary modern structure that has transformed one of London's most important old buildings.